Welcome to tonight's session on acids and bases. This is for organic chemistry students looking to get a foundation in this topic. So let's jump right in. What is an acid and what is a base? Well, starting with the Arrhenius definition, an acid is something that gives you an H plus in H2O, meaning it dissociates in water to give you that H plus. And a base is something that dissociates in water to give you an OH minus. But then I see a Bronsted acid is a proton donor. Okay, so what happens if we don't have water as the solution? Then we go to the next definition, and that is the Bronsted-Lowry acids and bases, which give us an H plus in any solution, or something that will accept H plus in any solution. So if you look at the OH minus, that technically accepts H plus in water, but with a Bronsted-Lowry definition, it could be alcohol. It could be ammonia. But then we have the question, what if we don't have this kind of solution at all? What if there is no H plus? Then we get a third definition, and that is the Lewis acid or Lewis base. And that has to do more with the electrons. So I think of Lewis as, we'll throw in that E, but Lewis for electron. A Lewis acid is something that accepts an electron pair, and a base is something that donates an electron pair. So what are we talking about? If you're just joining or watching the recording, welcome. Let's see, right there. All right, for a copy of today's session notes, for practice and more, make sure you go to layforsi.com/orgolive or see the pinned comment, because I'll send you a copy of everything that I'm writing today. And at the end of today's session, I'm also going to talk about my new acid-base study bundle if you're looking for more practice. So going back to the definitions here, we said that an Arrhenius acid is something that gives us H plus in water, for example, H2SO4. An Arrhenius base, something that gives us an OH minus in water, for example, NaOH. For the Bronsted-Lowry, I can still have that H2SO4 as my acid, but this time, perhaps I put it into an alcohol, or I put it into ammonia. For example, ammonium something, that's an H plus donor in solution. And the base, well, what can accept an H plus in solution? Well, that alcohol can probably still accept it. If we have, say, the CH3O minus CH3OH, that would be the base in solution in the alcohol solution. In the case of ammonium, NH4 would be positive. I can have an NH3, ammonia, which would accept an H plus in solution, or even one more, NH2 minus. Now, these should be review from what you've already covered in general chemistry, so I'm kind of flying through it. The Lewis acids and bases you're probably not as familiar with. These will come up more in the later orgo reactions. For example, if I have something like FeCl3, you're going to see these in your aromatic reactions. You'll see BH3 in a lot of reactions, starting with the alkenes, and you're going to see acetone as a common solvent. And for the Lewis bases, well, you're going to see something like a Cl minus, which is typically not a good base. Probably shouldn't use that example. Let's think more of something with a pi bond, like an alkene. That is going to come up in these reactions again, which is all really nice and good for the advanced reactions, but you don't have time to go through all these definitions in organic chemistry, and your professor is probably not looking for these definitions either. So what you want to look at here is kind of take a step back and ask yourself, what is the pattern? What is the similarity between the different types of acids? And what can I do with that? What can I take away as a simple explanation of the acids and bases? So here's what we'll do. Let's look at them one at a time. If I have H plus in water as my Arrhenius acid, for example, the H plus in H2SO4, the charge here, well, it's positive. If I have a Bronsted-Lowry acid, something that gives up a positive in solution, once again, the charge is positive. And if I have something that accepts an electron pair, it is attracted to negative electrons, wouldn't the charge be positive or partially positive? So if I completely ignore the definitions for acids and bases and just look at the trend, positive, positive, partially positive. I don't know why I put a negative there. I meant to put a partially positive. An acid, as a very simple takeaway, and what I want you to focus on today, is that the acid is something that is positive or partially positive. If you're dealing with something that is where you have, say, a negative and a more negative, you're looking for the more positive of the two. So it's the more positive within that reaction. Now let's jump over to the bases and see if we can find that same pattern. If I have an OH minus in solution, the charge on an OH minus is minus. Something that accepts an H plus in solution, well, if H plus is positive, it would be a negative that accepts a positive. So right there, we have a negative, we have a negative. We're looking for something negative or partially negative. And if I look at the Cl minus or the pi bond, that's quite electronegative. Well, look at the trend in your bases. You have negative, negatives, and negatives. The base is something that is negative or partially negative compared to the other thing you're looking at. So a base is going to be negative or partially negative. In organic chemistry, when you're not looking at tables and math and calculations, I want you to focus just on this. Let me know in the comments if you've ever noticed this pattern before, if it's ever connected like that. And then let's see what to do with this definition. If I take a molecule like water, what if I give you a molecule, water, H2O, and I draw it out? So I have an oxygen bound to two hydrogens, two lone pairs. Is water an acid or a base? If you're looking at water and you're thinking, okay, you told me positive or partially positive, negative or partially negative. I don't see any kind of charges here. What do I make of water? Well, let's see. I have a partially negative oxygen, partially positive hydrogen, and partially positive hydrogen. Water is neutral, but it does participate in reactions. And so, even though water is neutral, it can still be an acid or a base. It can be both. Let's take a look at how it can be an acid and how it can also be a base. To do that, we first have to go back to the definition. It's not positive or partially positive, but rather it's more versus whatever you compare it to. So let me show you a couple of reactions to help you make sense of what I just shared. Let's start with a reaction that looks like this. If I have H2SO4 reacting with H2O in equilibrium with HSO4 minus and H3O plus, we already said that H2SO4 is an acid. And when an acid reacts with something, we get an acid-base reaction. That means that water in this case has to be the base. And when the H2SO4 loses a proton, it's going to form a conjugate base. And when the H2O accepts a proton, it forms the conjugate acid. So in this reaction, water, neutral water, is acting as a base. What if I take a reaction that looks like this? In this reaction, I have NaNH2 reacting with water in equilibrium to give me NH3 and OH minus. Once again, water is starting out neutral. But if you look at what we have here, Na plus is a positive spectator. NH2 minus, that is a very, very strong base. That means if this right here is my base, then water in this case has to be an acid. That means the OH minus has to be the conjugate base because water losing an H plus gives me a base. And then ammonia in solution happens to be my conjugate acid. The base reacts to give me a conjugate acid. The acid reacts to give me a conjugate base, and it happens the same way for the other reaction. Same molecule of water, neutral in both cases, In one situation acting as an acid, in the other one acting as a base. Question: why wouldn't the charge apply to amino acids? I'm not sure I understand your question. So amino acids would have, so I think you're talking about the acidic and basic side chains. And so when you're looking at a negative side chain and calling it an acid, it's the conjugate base. I'm sorry, you're calling it an acid. It's the conjugate base of an acid. So for example, aspartic acid is an OH, neutral. Aspartate is the conjugate base of aspartic acid with a negative charge. So let me know if that answers your question. That is a really good question. A lot of students confuse that because the charges appear to be backwards. But going back in this case, one reaction that kind of sums this up is the autoionization of water, which you'll remember is H plus, H2O breaking down into H plus and OH minus. So you actually get both from water depending on the context of the situation. Now in Gen Chem, when you looked at this, you had a ton of math. You had pKa tables that you had to look at. You had all those ice charts to calculate. Let me know, give me a heart in the comment if you are done with calculations and ice charts and math and you want to see just how to calculate the basics. What do I make of acids and bases without any of the math, without any of those tables? Question: why oxygen is partially negative in water? I don't understand that part. So let's go back here. What we're looking at here is a polar covalent bond. So this right here is covalent. The oxygen and hydrogen are sharing electrons in the bond, but they're not equal, meaning the oxygen, because it's so electronegative, is pulling and pulling and pulling on that bond strength. The hydrogen has all its electron density taken away from it, and that leaves it partially positive. The oxygen, with all that negativity concentrated on the side, is partially negative. So that's how you get the partial charge, even though the overall molecule is neutral. Let me know if that answers your question, because that's a really good question in terms of, the molecule is neutral. So what's going on there? Sequoia says math is gross. So let's take a look at the no math approach to ranking acids and bases. In organic chemistry, you have to think. You have to reason through these concepts, and you're going to have to rank from the perspective of what makes something strong. What makes something strong? So the question is, what makes a strong acid or a base? What do you think? Let me know in the comments. What makes a strong acid and what makes a strong base? To answer the question of what makes something strong, let's go back to what makes the thing what it is. If an acid is something that is partially positive or positive, and these different types of acids want to give away their protons, then if an acid is something that gives away a proton or accepts an electron pair, then what we can say is the more likely it wants to do the thing that it's supposed to do, the stronger it is. The more likely a molecule is to give away a proton, the more strong it is. That makes no sense in English, but the more likely it is to give away a proton, the stronger it is, because that means it wants to do its job. Your job is to give away a proton. You want to do your job? Good job. That's something strong. If your job is to accept a proton, meaning to have a negative charge that can accept a proton, and that applies to these two, or to donate your pair of electrons to accept a proton, the more likely you are to accept a proton, the better you are at your job. The better the base is at being a base. I've been dealing with my toddler all evening, and I'm still thinking in toddler mode. You want to accept a proton? Good job. Oh my goodness, you did not want to go to sleep tonight. So when we're looking at a strong acid, it's very simple. A strong acid wants to give up a proton. The more it wants to give up, the stronger it is. And then where did it go? A strong base is the flip side of that. It wants to take a proton. The more likely it is to take a proton, well, the stronger it is as a base. So I see a couple of additional comments, and I want to go through them because this will be critical to the next step. The stability of their conjugates is partly how we define what is going on here. So that brings up the question of, well, what makes it want to give up a proton? And to answer that question, I want you to consider, this is not just for organic chemistry. You're going to hear me say this in a lot of the chapters this semester. And you're also going to, you're also able to apply it not just to chemistry, but to life in general. If something is happy, it is stable, it is unreactive. If a molecule is happy, it doesn't want to change its state. If you don't have an exam tomorrow and you're sitting on the couch, scrolling on your phone, you're stable, you're unreactive, you're not getting up for anything. But if you have an exam and you're stressed about it, you're unstable, you are reactive, you're going to get up, you're going to go study, you're going to do something to change the situation that you're in, because that situation is not ideal for the moment. And if we apply this to the molecules, then going back to who had said that, the stability of their conjugates is one way that we are going to evaluate. So what does that mean? If I have a molecule A, and in this reaction, molecule A goes to give me B and C. If B and C are very, very unstable, is this reaction likely to form? If A, that is happy, is going to break apart to give me B and C that are very unhappy, this reaction is just going to reverse itself. It doesn't want to form something unstable. But if, when A dissociates into B and C, we get B and C that are happy, they want to form, they want to be B and C because that makes them stable, then this reaction is likely to happen. The more likely the reaction is to happen, the more likely the molecules want to do that. That is the key to understanding how to rank acids and bases without a table. So let me know if you have any questions on this, and then we'll jump into the specifics for it. All right, so I see the number of protons it can release and how easily it releases. So typically when you have multiple protons to release, the first one is easy, the second one is harder. So it's not so much about how many protons, but rather how likely it is to release that one single proton. Conjugate base attached to a highly electronegative atom. So we're going to talk about atoms very shortly. Some molecules have total dissociation. So let's look at that as a specific example. If I have an acid like HCl, HCl is a very, very strong acid. And unlike a lot of the other acids that we're going to see today, this one gives you total dissociation, practically 100%, because Cl- is so stable, so unreactive, it has no desire to grab that H plus and reform HCl. But if I have a weak acid, it does not want to dissociate. Aaliyah, yes, this is typically covered in Orga 1. So famous Julius, we are about to jump into exactly that. So how do we know, and what are we going to look at? First, I'm going to give you a couple of rules. The rules to figure out which is the stronger acid or base. Number one, you want to compare your reactants. And what you're looking at with a reactant is very simple. The most unstable is your strongest one. Okay, so what are we talking about here? If the reactant is unstable, it's unhappy, it is desperate to change its situation. And if you can compare two reactants, you say this one is less stable, this is the stronger acid. Or this one is the less stable base, it's the stronger base. But if you can't tell, because sometimes they look pretty similar, if you can't, that's supposed to be a T, if you can't tell, then you look at step 2. And step 2 is you're going to deprotonate if you're talking about an acid, or protonate if it's a base. and then compare the products. Okay, I know this is very hypothetical, so let's turn it into very specific examples, and we're going to use the mnemonic CARIO. So a lot of professors teach ARIO. I teach CARIO, and if your professor's teaching CARIO, you know they've watched my videos because I came up with this one. And CARIO stands for the following: C-A-R-I-O. C is for charge, A is for atom, R is for resonance, I is for induction or the inductive effect, and O is for orbital hybridization, which we'll explain in a moment because that one is the hardest one. So we're looking at charge, atom, resonance, induction, and orbital hybridization. Now, if you're looking at this thinking, uh-oh, this is heating up, this is getting very tricky, I've got you covered. In addition to what I show you today, because I'll show you a couple of examples, I also have a practice quiz where you can do even more problems to work through each item on the list, everything that we covered today. And to get the quiz and a copy of my session notes from tonight, just go to or go live. The link is in the pinned comments as well, and I'll send you everything after we're done. If you're watching the recording, just sign up and you'll get an automatic email with links to everything. So let's jump into the first one, and that is C, which stands for charge. The easiest way to identify if something is strong or weak is simply to look at charge. Charge is a burden. Molecules do not want to carry a charge. They want to be neutral. They don't want to carry that kind of burden. So what do we look at for charge? Very simple. The atom that is the acid or base in question, if you compare them and it's the same atom, one is charged and one is not, the one without the charge is more stable. So for example, if I compare the molecule H3O plus compared to, say, H2O, which one is the stronger acid? Well, look at the charge. Remember, when you're comparing, what you want to see is not so much the charge itself, but the more positive of the two. So the more positive is going to be your acid, and the more negative is your base. And I'll show you a couple of examples that help make this clearer. But right now I have an H3O plus and an H2O. H3O plus, this is +1. H2O, this is neutral. Which one is more positive? H3O plus. That means of these two, this right here is my stronger acid. So how is a professor likely to test this? Well, you may see a reaction that looks like this. Let's see. H3O. Trying to think of an example where this would work. NaOCH3 reacting with H2O, potentially in equilibrium with CH3. I'm jumping ahead of myself. This is too advanced for what we're doing right now. If someone reminds me, I'll bring this one up again. I can't think of an example right now without going into some of the more advanced stuff. So let's just leave it very simple. H3O plus versus H2O, that's the stronger acid. But what if I give you H2O versus OH minus? And again, I ask you, which is the stronger acid? Well, I said positive or partially positive is an acid, but I have nothing positive here. I have water, which is neutral, OH minus, which is negative. That's fine. H2O is neutral. OH minus is -1. Which is more positive? Well, 0 is more positive than -1 because 0 is a higher number. That makes this one the stronger acid. Now, if you're thinking, wait a minute, Leah, that makes no sense. You're comparing a neutral water to OH minus, which is most obviously a base. Yes, a lot of reactions that you're going to see later on will take place in a basic solution, and we are looking for the acid in that basic solution. So for example, if you are dealing with substitution elimination reactions and you have an NaOCH3 and it's dissolved in a solution of CH3OH, we're not going into the reaction itself right now, but what I want to focus on here is you're looking at the acid in this solution. There are no acids. This is a base. OCH3 minus, most definitely a base. But the acid, when I need the source of protons in solution, it's going to be the CH3OH, because by comparison, I have Na plus positive spectator. That's a minus. The charge here is negative. The charge here is neutral. And 0 is greater than -1. This is my acid. This right here is not my acid, so it's my stronger acid. For students who are already in Orgo 2, you probably understand what I'm talking about in all those basic solutions when you need a source of H+. But for everyone else, just kind of keep it at this level. And let's continue. Okay, yeah, Aaliyah, I'm not sure I see what you're asking. So if you clarify your question, I'll be happy to respond. Let's move on then to A. A is for atom. If I'm looking at a situation where the charge is exactly the same, so this is where I had started writing and I realized I was giving you something with the same charge but something else going on. For example, if I give you a reaction, actually I think I wrote them out, that looks like this. I have 3 different molecules, and my question to you is, of these 3, which one is the stronger acid and which one is the weaker acid? Specifically, the acidic hydrogen is the red one that I'm showing you right here. If you think about the rules I gave you for ranking, I told you that the first step is to compare the reactants, and the most unstable is the strongest. But I'm looking at the atoms, I'm looking at the molecule, and they're all neutral. Nothing appears to be unstable. And so I go to rule number 2, deprotonate the acid and then compare the products. So let's see what this looks like if I deprotonate and then compare. All right. So for my green molecule, my ethane, I'm left with a negative carbon. For my methylamine, I'm left with a negative nitrogen. And for my methanol, I'm left with a negative oxygen. So these are the 3 molecules, and now that I have a charge, I can compare. So remember CARIO, we said CARIO. C is charge. Well, the charge is -1 for all of them. It doesn't help me if they're all the same. I need to look at the next piece. The next piece is A. And what you have to consider here is the electronegativity. So on the periodic table, even though you are given one on your exam, I'm going to ask you to memorize the following. H, C, N, O, F. Let me know in the comments if you've already memorized these. Under, we have phosphorus, sulfur, going down with the halogens, chlorine, bromine, and iodine. Just these 10, that's all you want to remember. The reason this is so helpful is you can know your valence electron numbers. So you have 4, 5, 6, 7. And the 2 trends that are really important are electronegativity, goes up and towards the right. That's the one we care about today. And size is down and towards the left. But the electronegativity is the one I'm looking at. If you have not memorized it yet, let me know in the comments. Do you commit to memorizing them as early as tonight? Julius, which clue specifically? And then looking at this right here, the best way to memorize that I recommend, layerforsci.com/memorize. I have a video that teaches you my approach to active memorization. This is how you'll remember this. Very, very easy. Sakura, I love it. And I want you to approach 15 minutes tonight. That's all it'll take, and you will have this. So what you're looking at is with electronegativity, it tells you how strongly the atom wants negativity. Oxygen, being the most electronegative, desperately wants electrons. Nitrogen a little bit less, carbon a little bit less. But electronegativity goes up towards the right. That means if I go down the periodic table, oxygen compared to sulfur, oxygen is stronger than sulfur, again, because it's higher up. And so using this, and the three atoms I just gave you are C, N, and O, where O is most electronegative and C is least electronegative. So let's see. If this is least electronegative, do you think the carbon will be happy or unhappy with a negative charge? Think about it. If oxygen, let's jump down, is the most electronegative, that means when it finally gets the negative charge it was looking for, it's going to be the most stable because it is most capable of holding that charge. But carbon is the least electronegative, and that means you give an atom that does not want negativity. You give that atom a negative charge, it's very, very unhappy. That means this is going to be least stable. It's most unhappy. I'll just put most happy. And so even though we couldn't tell from the neutral molecules which one is happy or unhappy, we can very easily tell on the product side. If carbon is least stable, most unhappy, it does not want to form. Like my toddler at bedtime, kicking and screaming and stalling. My goodness, this kid is so creative at coming up with reasons he does not want to go to sleep or daycare. That's a new thing. He doesn't want to go. Carbon, kicking and screaming and coming up with excuses. It does not want to form. So if it doesn't want to form, this reaction is much more likely to go that way. And that means this is your weakest acid. Kicking and screaming, not happening. But this one right here is like my toddler on the weekend going to Stu Leonard's. If you guys have a Stu Leonard's, let me tell you, I never appreciated interactive supermarkets as much as I do right now. My kid loves it. They have singing avocados, a cow, just this like cow head where he goes in and pushes the button. If somebody reminds me, I'll post a video or I'll post a picture of him pushing the button from this weekend. And the thing just goes, moo, and he comes running, screaming, I pushed the button. This one is so excited, like my toddler going to Stu Leonard's. It runs to the car because it wants to get there really, really fast. That makes it the strongest acid. So again, even though the neutral ones you cannot tell, if the conjugate is happy, it's likely to form. Weakest acid, strongest acid, simply by looking at the products. Does this make sense in terms of how we compare and how we rank them? And your professors may give you the question in this form, or you can see the same exact question written out like this. If you have NaOCH3 plus CH3CH3 in equilibrium with right at the way you're likely going to see it, CH3OH plus, and of course I'm running out of room, NaCH2CH3. This looks completely different from the problem I just gave you. And so here's how you would break it up using the same exact scenario. First, you realize that Na plus, whoops, did not mean to do that. You realize that Na plus is a positive spectator for the OCH3 minus. And again, positive spectator, in this case for the CH2, CH3 minus. Then you pair them up, and all you have to do is find what's matching. I got an OCH3 here, and that's an OCH3 here. So that these two are conjugates, meaning they're a conjugate pair. The more negative of the two is the base. So that means that this right here is the base. This right here is my conjugate acid. And if I do the same thing up top, then I have, this is just my carbon chain. One has a charge, one doesn't. The more negative of the two is a base. So that would be a conjugate base because it's in the product. I don't know why I said base, I wrote acid. Conjugate base, because I started looking here. And this one is the acid. Once you've identified the pairs, the easiest way I find to predict the position of equilibrium is to find the position of the negative. Or rather compare the stability of the negatives. And that means I'm comparing the OCH3 minus to the CH2CH3 minus. And now I say CARIO, C, charge. They're both negative. A, atom. What I'm really comparing is an oxygen atom, that color does not show up on the screen, an oxygen atom to a carbon atom. Oxygen is more electronegative. That means oxygen is more stable with a negative charge. This reaction will favor the reactants over the products because it's more stable with a negative oxygen than a negative carbon. So do you see how I gave you the same exact problem, the same exact ranking, but in a slightly more, like I find this more difficult just because it's not as obvious what it is that you're comparing. If you're liking this so far, if this is clear, let me see a couple of hearts in the comments and let's continue. All right, I see a couple coming in. What if I give you a reaction to compare? And this time we're looking at, did I draw this one out? I did not, so let me just draw it out right here. I give you a molecule that looks like this, ethanol, and one that looks like this, ethanoic acid. We're looking at the list for CARIO, and we already know that C is charge, everything is neutral. A is atom. Well, first we need to know what our acid is, so I'll change the acidic proton right here. The atom holding that proton is on oxygen. Same exact thing. I can't do anything with A, but my next one pays off. R is for resonance. So before we go into the reaction itself, I want to talk about resonance itself. What is resonance? When you think of resonance, you hear the word to resonate. What resonates? You like what I did there? What resonates with you when you're thinking of resonance? I think of it as just something going back and forth, back and forth. So when we're looking at resonance in the context of organic chemistry, just think of it as sharing a burden of charge. If you have a burden of charge right there, this is charge, and it's really heavy. The molecules do not want to carry it. It's very heavy. Option 1, carry it by yourself and struggle with it. Option 2 is you get a friend to help you carry it. Hopefully a very strong friend. And now that weight is distributed between the two different. Let's make them so happy for sharing. These do not look like people. They look really scary. Let's try that again. Okay, they don't look happy. One of them got roped into sharing this burden of charge and they're not very thrilled with you, but we'll take it. Now that it's distributed, we have potentially 50-50. That burden became a lot lighter. So let's go back to the rules I said before, where if you cannot tell what's going on from the reactant, deprotonate and look at the product. If I deprotonate the first one, minus H+, what I'm left with is an oxygen with, we'll give it that extra lone pair and a negative charge. If I deprotonate the ethanoic acid, I get the same thing, oxygen with that extra lone pair and a negative charge. But the first one is stuck carrying 100% of the burden of charge. Oxygen is holding it. That's it. No help. The second one is able to resonate. The resonance can go this way and that way. So if we show this resonance here in more detail, if I have a molecule that looks like this, and now watch what happens to the electrons. We'll make these pink. These go here. We'll make these green. They go up here. Show the resonance arrow like this to show it's going back and forth. What I actually have is a lone pair, well, the one that was the pink lone pair is now sitting as a pi bond. The one that was the green pi bond is now sitting up here. And then I have the electrons here and here, like that. What about my charge? That is key. That's negative, and that's negative. That means I have 50% of the negativity held on one oxygen, 50% held on the other oxygen. Which conjugate, with this in mind, which one do you think is more stable, given that one is stuck carrying the entire burden, but the other one is sharing? Well, the one that is stuck carrying the entire burden is very, very unhappy by comparison to the one that is sharing, that is more stable. The one that is more stable then is the stronger acid. The one that is less stable is the weaker acid. So that gives us the R for resonance. Arpit, which part did you want? Oh yeah, that's a good point. Good feature of YouTube. At any point you need me to repeat something, you can just rewind. I totally forgot because I used to do these live streams on another platform that you couldn't rewind. So absolutely. So the bottom structure is more stable. Absolutely correct, because of the resonance. So seeing that the carboxylic acid is the more stable, or is the stronger acid because it gives you the more stable conjugate base. What if I give you a carboxylic acid that looks like this? And let's put the acidic hydrogen in red. And I ask you to compare it to, well, another carboxylic acid, only this one has a chlorine right here. Which one is the stronger acid? Or if you're not sure, which conjugate base is stronger? Let's see. We have the mnemonic CARIO. And so we'll start with C for charge. There is no charge. Well, let's see if I can induce a charge by deprotonating both of them. Minus H plus, minus H plus. And what does that give me? Oops, did not need to pull the oxygen off as well. What I have is a negative oxygen and the negative oxygen. The charge on the reactants and the product, exactly the same. Next, I look at the A, atom. The atom holding the charge, oxygen and oxygen. Once again, exactly the same. R for resonance. Well, we already know that this can resonate like this, but so can this one. They can both resonate. So again, we have no difference yet. And so we move on to I. The I in CARIO stands for induction, or the inductive effect. Now this one is a little bit harder to understand compared to what we've done before. And so the way I like to think of the inductive effect is less physical help and more moral support. If you have to do something very difficult, say you have to carry something really, really heavy, then having physical support is obviously the best kind of help you can get. But if you have to do something, let's say, I don't know, you're moving and you have to carry furniture and it's really heavy, and you have a 5-year-old child, nephew, niece, or neighbor who wants to help, but you're not really going to let a 5-year-old carry furniture. But if that 5-year-old, assuming you love this kid, is standing on the side. So today at the dinner table, after my husband finished his food, he takes his plate and walks to the kitchen, because we're trying to teach my son that after you finish, you take your plate to the kitchen. And he just starts shrieking because, Daddy, yay, you take your plate to the kitchen, yay. And he's just shrieking at the top of his lungs. No one has ever congratulated someone more for taking a plate to the kitchen. That kind of moral support, my husband didn't need help carrying his plate. And he could definitely carry it on his own, but I think he felt a drop happier and a drop more motivated. It was just, we were in middle talking, and just out of nowhere, he starts shrieking that something happened. But he was just clapping for my husband taking his plate to the kitchen. Having moral support when you cannot have physical support is the second best thing. It helps a little bit because it helps with mindset, even if it can't fully help with the thing itself. Yes, I love him so much. That kid is a riot. That throat's starting to bother me. That's not good. So what we're looking at in context of moral support for molecules is having something like chlorine nearby. It can't help with resonance. It can't change the charge. But because it's highly electronegative, it pulls just a little bit of negativity away from the other part of the molecule. So it's pulling it and pulling it and pulling it. And so if we're looking at the conjugate and we have the negatives resonating back and forth over here, and a little bit of negativity is being pulled towards the chlorine, then this is ever so slightly more capable of throwing negativity into the molecule because some of it is being drawn in the direction of chlorine. So the inductive effect is just kind of pulling on the electrons a tiny bit and therefore making it more stable compared to not having anything. Well, let me clarify, because some professors will trick you and they'll throw a hydrogen on here. And you'll ask yourself, wait, how does a hydrogen react? Well, don't forget, there's hydrogen everywhere. In skeletal structure, if you don't see an atom, it's a hydrogen. So it's really a question of an atom of value, an atom that can actually pull versus one that cannot. And chlorine, fluorine, these atoms, if they're one or two positions away, can pull and therefore make this a little bit more stable. And if this is a bit more stable, then the inductive effect gives you a stronger acid because it helps stabilize, ever so slightly, helps stabilize that conjugate base. All right, so then what if, let's try a different one. What if I give you a reaction that looks like this? Whoops. So I have these two molecules that I'm comparing. And what I'm looking at is, well, let's start with CARIO. I have C for charge. I have none. It's a neutral molecule. A for atom holding the proton or the charge. In this case, I have a carbon and a carbon. Nothing for me. R for resonance. I have pi bonds here, but they cannot resonate. It's just the triple bond. I for inductive effect. I have nothing nearby. So that doesn't do anything for me. But what I do have is a difference in the orbital. O stands for the orbital hybridization. And what I'm looking at specifically is the difference between having an S versus a p orbital and how much S versus p. So let's move the example down. Come on. Why is it not letting me do that? There we go. All right, let's move this down and let's talk about the hybridization for a moment. The technical explanation behind this is not something that I think is typically taught in organic chemistry. So I'm going to tell you how I think about it, and then you let me know if you find that helpful or not. But for me, this has never failed. When I think of the s orbital, think of your hybridization where you learn S, P, D, and F. And S is that little sphere on the nucleus. The P is when you have those shapes going in all directions. So S is closer to the nucleus. But if you have a p orbital, don't forget that you have this direction in the x, this direction in the y, and then you also have, going back and forth, that's the z direction. So you have all the different shapes. And if an electron is held in the p orbital, it's not as close to the nucleus. And this is key. if you have an electron that is being held closer to the nucleus, don't forget, is positive, then if it's closer to the nucleus, that negative electron is balanced out by a positive nucleus. But if it's further away, it's not being held as close. Okay, so let me know if you're with me so far. S, I bring the electrons closer. P, the electrons are further away in those bubbles, just going around and around in figure eights like that. So what does that have to do with the hybridization? If S is closer to the nucleus, then we can assume it holds the negative better. And this one is not as good holding the negative. It's like letting my toddler bring a full cup of water to the table. Hint, it didn't wind up on the table the way we wanted it to. We had a very stressful evening. Let's just put it that way. So let's move this example down a little bit more and take a look at the different types of hybrids you're going to see with S and P. This is really not in a good place. I'm just going to move this all the way down. Okay. When I'm looking at hybridization, the three that you have to know are sp3, sp2, and sp. With an sp3 hybrid, you have S, P, P, and P. That's how you get sp3, S and 1p and 2p and 3p. If you look at what makes up that sp3 hybrid, you have 25% of that orbital is S, and 75% of that orbital is P. If you look at an sp2 hybrid, that's S, P, and P, that means your S is a third. 33% S, I'm trying to make my S's not look like fives, and 67 or 66.66% P. And finally, if we're looking at SP, that's just S and P, which means I have 50% S and 50% P. Now, if the S orbital is better at holding a negative, then the one that has more S is better at holding a negative. Well, the most S that we have is 50%. That's high S. That would give us the strongest acid because the conjugate base is going to be best at holding that negative charge. Holds negative the best. But if we look at this one right here, which is very low S, it's only 25%, that means the sp3 is worst at holding the negative. And that is what we have to compare. So if we look at the example and we have, well, they're just neutral hydrogens, let's deprotonate and see what that gives us. If I pull off the acidic hydrogen, that means I take off an H+, take off an H+. What do I get? Well, first we get a negative charge and a lone pair on each carbon. But now, look at what I have. The carbon holding the negative, that is sp. That is 50% S. The carbon holding the negative here is sp2. That is 33% S. That means this one right here is the stronger acid because it's doing a much, much better job of holding that negative charge. Once I have the negative there, it holds it much closer to the nucleus because it has more of that S orbital. And that makes this one here the weaker acid. And if I had given you one with sp3, for example, just a CH3 like that, like we saw before, and pull away that H+, this would be your weakest acid. I already have the rank. So we're going to call this the mid weaker acid because I just threw in a weakest. Weakest acid right there. All right, so that was an overview of the CARIO mnemonic. But I didn't give you a lot of practice here because the first step is to understand what is going on, to make sure that you know how to apply the mnemonic. And the next step for you is going to be to practice. For a copy of today's session notes and practice for CARIO and more, make sure you see the pinned comment or go to layerforsci.com/orgolive. Now, this was just an overview. The next step is practice. So with your permission, I want to take a few minutes to discuss the new acid-base study bundle. This is the first study bundle of the semester that I've put together. And the goal with this is to give you a lot more help with a specific topic, for example, acids and bases, and guided practice to make sure that you can do as well as possible on this topic. All right, so for the acid-base study bundle, what you'll get is the following. I have an acid-base quiz on my website. So what I want you to do is first start with a quiz. And on my website, you'll also get the PDF solutions. But then, here's the thing. The PDF solutions just give you the answers. In the acid-base bundle, you're going to get a step-by-step guided walkthrough. Here's the question. Here's what we're looking at. Here's how to think about it, with questions ranging from beginner to medium to advanced, to make sure that no matter how your professor presents it, no matter how much your professor tries to trick you, you know what to do, how to do it, and of course, the right answer. So that is the how-to video solutions. And then I'm also including even more acid-base practice. So the link to sign up is go to my website, layerforsci.com/CARIO, exactly what we've been working on today. And you can sign up and get started. So the link is layerforsci.com/CARIO. Question, can we access this via the study hall? Yes, the study hall includes all of these videos already, but if the study hall doesn't work for you or if it's something you're not interested in, then you can get just the study bundle for this one topic.